gravitational potential energy. But yes, if you have a case like this one, okay, then you have yi here, okay, then you can have what we call it, just gravitational potential energy at this point. But right now, gravitational potential energy is zero because you are on the horizontal surface. Now that is 0 plus half kx square is 0. Only energy is this one. So the other two are 0. Only total energy is simply equal to the kinetic energy maximum. Now, when you are in between, you have some value x, right? X is not 0, x is not maximum, keep in mind. So once you have some x value, you'll be having half kx squared potential energy, the spring potential energy. Similarly, velocity is not 0, it has some velocity 0, so half mv squared. So the total energy at this position, anywhere between 0 and any x value, this side or the other side, you have this relationship. Now, once this compresses the spring to the maximum, so x is maximum. X maximum, I told you, we call it amplitude. Okay, so now velocity becomes 0 at the end and x becomes maximum. So half kx square or half k a square, because maximum x is a. So this is the total energy in this case. Again, once it goes there, it goes to the left side, minus initial. This side plus initial, minus initial. But it makes no difference because this is square of the initial velocity in this energy. So this is how the energy is transformed from one type of energy to other and in between. Right? Okay. So let's discuss this example. Yes, you have A and B part only. So a car, 13,000 Newton. It's not kg, keep in mind. This is not the mass, this is weight. Weight is equal to mg. Starts at rest on the top. Okay? Now, y initial height 10 meter rolls down from a height of this initial height, as I told you. If it then moves across a level surface and collides with the light spring-loaded guard, so this is your spring with spring constant K. K is given to you in Newton per meter. A part, neglecting any losses due to friction and ignoring the rotational kinetic energy of the wheels, we ignore these things. Find the maximum distance that once the car reaches here, it compresses the spring. How much that spring is compressed? X, you have to A part first. first. You have to find out X. You know, total energy initial, total energy final. Okay, so half mvi square plus mgy half kx square half mvf square plus mgyf plus half kx square. Fine. Okay, starts from rest. Spring is far away, so no compression, no extension. This is 0 again. So you are left with this on the left side, and on the right side you have this 0. Y final, once you are coming down, height is decreasing. At this point, height becomes 0. Good. So you are left with this one. Final or simply X, whatever you call it. So, yes. So I can simplify it now. This is mg. So X square is equal to 2 mgyi and 2 divided by k, and then I can take the square root. Let me come over here. Right, so X will become 2 mgyi over k. 2 mg how much? Don't make mistake to multiply again with 9.8. It is already way given to you, not the mass. Mg 10 and k 6. So you get X is equal to, yes, how many meters? 0.5. Okay, so this is your compression once the car reaches down. Yes, next switch over to B part of the question. You have only a B part in this example with you. Yes, B part then. Calculate the maximum acceleration of the car. So A, you have to find out. So A is equal to, you have this rule, F is equal to minus kx. This is equal to ma. So A is equal to minus k over m into x. Right? Now, you are given mg. Can you find out the mass? Again, there are more than one correct formulas and the methods to do the question. So M, you will get yes, this mass I'll be using over here. K, right, and X you just finish. You get the acceleration, sorry, it's like a projectile, I'm sorry. Right, so acceleration will be 380. That's it. Yes, next topic is velocity as a function of position. So velocity as a function of position x. Just keep this in mind that you need to use the conservation of energy theorem to finally get, after simplification, the velocity on one side. On the right side you'll be having position involved, so it will be depending upon the position. Right. You see, you have, we have already discussed how we calculate the total energy at different points. One on the rightmost, one on the leftmost, one in the middle. As you know that on the rightmost, you have only total energy simply equal to the maximum potential energy, half Ka square, elastic potential energy. Okay, and similarly on the leftmost you have the same total energy equal to simply elastic potential energy. Okay, on the minus A side, because it's square, so it doesn't make any difference in the end. But in the middle, at x is equal to 0, you have total energy simply equal to the maximum kinetic energy, half mv square, the maximum. Because once you if you look again for your better understanding, so this is x is equal to 0, this is plus a, and this is minus a. Okay, once you are here, okay, at x equal to maximum, which is amplitude plus side, you see velocity becomes 0, and x maximum, which is a, so maximum elastic potential energy, which is the total, because once velocity is 0, kinetic half mv square is 0 at this point, right? Once you start moving on this side, velocity start increasing. When you just reach here, velocity is maximum, so kinetic energy is also maximum. And since x is 0, so x0 means elastic potential energy at this equilibrium position is 0. So only energy which is the kinetic energy maximum, it will be there as total energy. Once you start again, velocity is maximum, keep in mind here, velocity maximums going left, velocity starts decreasing, 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 again velocity becomes zero, like here zero, like here zero. But this is maximum but negative side. So velocity zero means kinetic energy zero at this point. Here kinetic energy is zero. Okay? Here you have potential energy is zero, but kinetic maximum. But of course, in between these two, or in between these two, you have both values. This is what I have here. Now, one side I have maximum, which is half K A square, maximum. Total energy, right? Because the maximum positions here and here, kinetic is zero, so total energy, this one. This total is equal to somewhere in between, so this is half Kx square plus half mv square. You have some kinetic, you have some elastic in between equilibrium position and the maximum positions, extreme positions. You need to find out, keep eyes on what you need exactly finally, velocity. So I take this on the left side and this one I will move it to the other side. So half goes with all half, so mv square is equal to Ka square minus Kx square. So K is common. Okay. Now this is v square. I take m here down, right? And finally, I get here v is equal to K by m under the root x square. Right. This is what I have already written here. The same thing, by the way. And keep in mind this K by m under the root, this is, we call it omega, the angular frequency. Right? So this is omega. You see, the last thing, so this is the same equation, I wrote it here by the way, nothing new. You see finally what we needed, velocity on the one side, on the other side function of x. Since amplitude is constant, it is maximum, K is constant, M is constant, so velocity only depends on the position x. Okay? Right. Now if x is 0, of course, which is in the at the equilibrium position, if x is 0, then you will be having V max is equal to K by M under the root A, which is K by M under the root is omega. So you can write this one as V max is equal to omega multiplied by A. So this is, about your final expression for velocity, this much. And for the maximum, you know that maximum velocity is at x is equal to 0. We have learned it before that at x is equal to 0, velocity is the maximum. This is what you need, this relationship. See you in the next lecture, second part of this chapter, inshallah.